right, and let me take you to the practice quiz, problem 1 for today. Let me just check, make sure my mic is on, all that good stuff. All right, so what two positive real numbers whose product is 50 have the smallest possible sum? And I'm going to ask you to do things in this order. Explore what this means, get examples, put them in a table, and then keep following the instructions on down and to solve this problem with a calculus method. You might be able to solve it without a calculus method, but also be able to solve it with a calculus method. And if I gave an exam problem for optimization, I would probably say something like in the directions, show that you can solve this with a calculus method, using calculus. Okay, so I'm going to interrupt you now, and the first part of examples, if I put my numbers really far apart, if I get them closer together, okay, then these, they had to be such that they multiplied to be 50. And the more that I put them, hold it, yeah, 27. Okay, now this is 51 when I add them together. This should have been, sorry, x plus y. Because they had to be such that they multiplied to be 50. That was the condition to be on this table. And then we're just looking at their sums. And if I just make a simple table like this, I get this observation that the closer the numbers are together, the smaller the sum is. So I don't want my numbers far apart. If I'm trying to get the smallest possible sum, I want to get them to be really close to the same size. Okay, so that's a conclusion that's very reasonable to come up with by experimentation and exploration. And now I'm going to give you a little more time to keep going with the calculus method of getting this answer. Again, the constraint equation is just that they have to multiply to be 50. That's a constraint that has to be satisfied to actually get onto the table. All right, anybody need more time? Because I'm going to race through the end of this. All right, so what am I optimizing? We're minimizing the sum. Minimize the sum, and we'll call it S. The constraint equation is x times y must be 50. And then the optimization equation is S equals x plus y. It has to meet this condition, xy is 50, and then trying to minimize S over here. The same problem that we always have is that S is a function of two independent variables. We need it to be a function of just one independent variable. So I take this equation, solve it for y, 50 over x. So S is equal to x plus 50. I'm going to write it as x to the negative 1. And then I'm going to minimize S. I'm going to guess that this is a graph that has a low point in it. ds dx is 1 minus 50x to the minus 2. And then I'm going to set this to 0 to minimize it. Bring the 50x squared over to this side. Hold it. Yeah. Is 1 over 50, yeah?
Shouldn't it be when you had 1 minus 50 squared and it should be negative 2?
Thank you very much. I knew something wasn't coming out right. This, I forgot my negative sign. So this should be 50 over x squared equal that. This isn't right. And then I cross multiply x squared equals 50, x equals, now it says what two positive real numbers. So although I could get a positive and a negative, I'll just use the positive, square root of 50. And then if that's a square root of 50, then the y is 50 divided by square root of 50, which is also square root of 50. So y is also equal to the square root of 50. And that's the two positive numbers. When they're exactly equal to each other, we will minimize this sum. And it makes sense from what we'd seen in the chart over here. So, give me a little feedback on problem number 1. Let's go to number 2. Find that integral, definite integral. Okay, speak up if you need more time. All right, let's go ahead and do it. The first step in many of these problems, or maybe most of them, is you let your u define what your u is going to be. Now before I do this, let me again hold it. I think we had written it. Let me be consistent. G of f of x prime of x dx. This is what we can integrate. If this is the u, this becomes the du. And we have to have a function and its derivative in there to be able to do the u substitution integration. And here we notice cosine, and its derivative is negative sine, and the du part has to be in the numerator. We couldn't start with the u being sine, because then the du would have a 2 added to it, and it would be in a denominator. None of that would work. So this is, and then I'm going to also insert, these are x equals pi, negative pi to x equals 0. So we're going to go with u being 2 plus cosine x du dx. The derivative of 2 is 0, is negative sine x. And then multiply both sides by dx. Du is negative sine x dx. Multiply by negative, negative du is sine x dx. Now, this part matches this right here. So I'm good to go. This is going to equal integral. I'm going to change my limits to u limits. And I'm going to rewrite the bottom as divided by u. And then the top, sine x dx, is the same as negative du. Okay. Now, let me, on this one, I'm going to show you what would happen if I, instead of doing u equals, if I had left it as x equals. Because it's possible to do it this way. Let me show you what would happen. I would get negative ln, because the integral of 1 over u du is ln of the absolute value of u. And then instead of plus a constant, we have these things evaluated. Now when there's a constant out front, like a negative sign, you can just factor it out. And then suppose we still had left these as x's. Okay, we'd have this. And then this would come down to, now we can't substitute those in. So we'd have to take this, since these are x's and that's a u, we'd have to replace u with what it is. U was, scroll up and look, 2 plus cosine x. Here ln, absolute value of 2 plus cosine x. Evaluated from x equals negative pi to x equals 0. Now, the largest, well, cosine x is trapped between negative 1 and 1. When you add 2 to it, you can never get a negative number. So you don't need these absolute values. When that's the case, we just drop the absolute value off. And then I'm going to have negative, and then when I substitute 0, I'm going to get ln 2 minus ln. Now when I substitute negative pi in there, a quick unit circle, negative pi ends me up over here. And the cosine of that is negative 1. Negative 1 plus 2 is 1.
For the natural log of 2 plus cosine, would that cosine of 0 is 1? Would it be natural log of 3?
Oh, cosine 0 is 1. That's right over here. Thank you very much. Saving my butt today. And this is 3, not 2. Alright, so this is, now the natural log of 1, saying e to what power is 1, e to the 0 power. So this is just negative natural log 3. Okay. Now, that's my answer if I did it staying with x's. Negative natural log 3. Let me show you how it would have gone quicker if I'd have changed the u's. Changed the x equal limits to u equal limits. When x is equal to negative pi, u is equal to, that's negative 1 plus 2, so this is 1. When x is 0, substituting 0 in, and you get 1 plus 2, and you get 3. If we'd have done it this way, then we'd have had u equal 1 to u equal 3. And then, instead of these extra steps, we'd have gone right to equals negative ln 3 minus ln 1. And notice it's the same thing, but it just gets there quicker. And that's why I prefer changing the limits instead of going back to x's and then resubstituting with the x's. Alright, so give me feedback on number 2, please. Kylie, right, not sure how you got trig functions to equal ln. Let's review that real quick. Alright, so let me enlarge this a bit again. Alright, so we did our u substitutions. And the u was this trig function, 2 plus cosine x. But then when we rewrote this, without using x anymore, there's no trig anymore. Now this is also the integral of u to the negative 1 du. And if you try using the power rule on the integral of u to the negative 1 du, you get u to the 0 over 0, which is illegal. And we remember the integral of u to the negative 1 du, or 1 over u du, that has to be this ln of the absolute value of u. Okay, so that's how we transitioned. And I like the way you're pointing out that we had trig functions. We changed it to a new integral. There are no trig functions. But all the trig functions disappeared. They did. And And then you
So
just,
maybe I'm not understanding how the trig functions disappeared. I understand you replaced 2 plus cosine of x with u on the bottom, but
yeah.
how did you get du to be on the top?
Okay, so u is equal to 2 plus cosine x. Take the derivative. Du dx, derivative of 2 is 0, derivative of cosine x is negative sine x. Then we multiply both sides by dx. We get this. And then I want to isolate, because the only thing up here is sine x dx. I want to get rid of that negative sign. So I multiply both sides by negative 1. So now this matches exactly this. So then I can replace what's in red up here, in red parentheses, with negative du.
So you're saying when you took the derivative of u, you replaced the numerator with du
That's right.
because sine of x dx is the same as sine of x over u times dx, which is over 1 as well. So that's saying sine of x dx over 2 plus cosine of x, right?
I
As a
got a little
fraction.
lost with your explanation, but
Well, the dx is being multiplied by the fraction, but the dx would be considered a fraction as well, right?
yes, you can think of
So the
dx over 1,
numerator,
so it really goes in the numerator, sine x
okay,
dx, yes.
okay. Oh, I think that's where I got lost.
Okay, gotcha. All right. All right, let me quickly check over here. All right, those were the only 2 problems in the practice quiz today. And let's go to homework questions. And one question was stated earlier, 27b. So let's look at 27b. All right, this is a real classic optimization problem. It's done in virtually every calculus class, some version of this problem. Basically, if anybody's gone through calculus, they've had this kind of a problem before. And I'm going to, well, so we've got our diagram here. Let me draw it a little bigger. Okay, and you got to go from a point out here, and you got to go to this restaurant. Here. And the boat from here to here, it's 4 miles. You're 4 miles straight out in your boat. And that point is 6 miles. So over here it's 6 miles. Straight along here to get to the restaurant. Okay. She walks at 3 miles an hour and she rows at 2 miles an hour. Alright. Now my first instinct would be, oh, just get to the shore as fast as you can. Because you can walk faster than you can row. And then walk the long distance and you row the shortest possible distance. but it doesn't turn out to be this way. When you're walking faster than you can row, you want to actually aim somewhere like they have, somewhere in between. And you won't add a whole lot of distance. This 4 miles might become just a little bit more than 4, but you'll cut off a huge amount of distance that you would have to walk, and then you walk the rest of this. You still don't row directly there, because you row so much slower than you walk. You go, 1.5 times faster when you walk. So this is, we're trying to find this optimal point at which we can do this. All right, now Josh, you were saying that you only had a question on part B. Were you okay with part A on this?
Yeah, I was.
Okay, so this, I think we're going to have to do part A though to really be able to get to part B. So if I'm deviating from the way that you were doing it, let me know. Okay, she
Okay.
walks, she rows 2 miles per hour. In this part, she goes 3 miles per hour. Okay, but I don't really want a miles per hour here. I want a distance here, and I want a distance here. And then if we can get this as a distance, we can answer the question, how far from here should she aim in order for this to happen? So how do I turn this miles per hour into a distance? I'm going to have to multiply it by how many hours. And let's say that she she would minimize the total travel time. All right, so we're going to have TR, which is rowing time. TW is walking time. The time that she's walking. And then we're going to be minimize T total time, and T total is equal to the sum of the other 2 times. And this is the same way we've done every one of these. 1 output variable, but 2 input variables. So we're going to have to rewrite one of these in terms of the other. It's kind of like that's an x and that's a y. We'll have to get some kind of a constraint equation, and then replace one of these letters with the other letter. And so this was 2 miles per hour times the time rowing times the time walking. Okay. And this would be in hours. Hours would cancel out. You just get miles and so on. And then I'm going to go to, if we get rid of the units, 2 time rowing plus 3 times the time walking has to equal the total amount of distance, because that's a distance and that's a distance, and they have to add up to okay. Now they don't add up to 6. What do they add up to? What do we do for a constraint equation right here? Anybody have any ideas? I'm kind of like, I got stuck here.
I didn't have them equal anything because eventually when you take the derivative, when you find your optimization equation, when you take the derivative, you're able to solve to find, like when you set it to 0, you do get a value. So I don't think you have to set it equal to anything.
You don't think this gets set to anything? Is there any kind of constraint equation?
I came up with, I took using the Pythagorean theorem. So I set like the one distance that you have in blue dotted line that's not red. I have that as x.
X.
And then the other distance was 6 minus x.
So you said this distance right here is x, and then this distance from here to here is 6 minus x. So if like x was 2 miles over, then this one would be 4, and they'd add up to 6 or something like this.
Right.
And
And then the total distance would equal the hypotenuse of that triangle plus the 6 minus x. And
all right.
and then I found the time in terms of the distance equals rate times time equation.
Okay, so instead of doing this plus this, which is my first instinct, and hopefully I got something like a nice easy number, but I found out, no, this isn't going to equal 6, so I can't do this. Instead, we do this plus this, but the x gets to be replaced. The x, 4 squared plus x squared equals the hypotenuse squared. 2 times the time rowing squared. So this becomes x squared equals 4 time rowing squared minus 16. So bring this 16 to the other side. So x is equal to, we know it's positive, so we only take the positive, 4 times the time rowing minus 16. So that's this one right here. So let's go to
Professor Shankin, I think you're missing a t squared under that square root.
thank you. Okay, then that, here is my constraint equation. Something that must be true. X plus 6 minus x equals 6. But the x we just found out was this. Now, hold on a second. These things would just kill each other off. I have a negative and a positive. This isn't going to work.
The way I did it, I mean, I was curious to see how you would do it because I felt like mine was really long and I was thinking there had to be a better way. But I took, so originally like x squared plus 16, I saw that as the distance that was the hypotenuse, and then 6 minus x as the distance along the shore. And I defined those as times, like based on their rate. So for example, the time going down the hypotenuse would be square root of x squared plus 16 over 2. And then the time going 6 minus x would be over 3. And then I took the derivative of that equation.
Yeah, that's how I did it.
Okay, so you don't really get necessarily a constraint equation on this. You just get the 2 times. So, the way both of you are telling me then looks like this, is if you take this triangle right here, you get this squared plus this squared equals this squared. You solve it for the, I'm lost a little bit. Solve it for the time?
Yeah, so if distance equals rate times time,
Yeah.
I figured that that I could define the time, the hypotenuse's time as the square root of x squared plus 16 over 2, because its rate is 2 miles per hour.
All right, so this is a distance right here, because that's a rate times the time. So the time rowing is whatever this distance is divided by the rate, 2. And then for that distance from here to here, you did what?
I did 6 minus x over 3.
Replace that.
Oh, wait, that's for the other line.
Yeah, the other one. Yeah, I didn't end up having to replace anything. That's the way I did. I didn't. That's why I was curious, because I thought I didn't know if I was doing it right, but it did give me an answer, and then it checked out. So I had 2 separate times, and the total time, because that's what we were looking for. Like, I guess to optimize the total time, I just added the 2 separate equations and then took the derivative of that and set it to 0.
Okay, so what does this distance then get replaced with? This is distance.
That's square root of x squared plus 16, because that's what that
Okay,
hypotenuse
because
equals.
you use the Pythagorean theorem on this.
Yep. Mm-hmm.
All right, so just between d4 and x, square root of 16 plus x squared over 2. So that's the time that it took to travel this one. Okay, and then the time that it took for this one is what?
6 minus x over 3.
Say that again?
It's 6 minus x over 3.
Because it's 6 minus x. All right, so that's the distance. And then times the rate equals the time. Okay, so then we have this time and we have this time both of them are in terms of a totally new variable, x, which was just a portion of the distance. But what that x was really what we were being asked to find. She walks 3, and at what point on the shore would she land to minimize the total travel time? So they're really asking, what is x? So I guess it makes sense to write it all in terms of x. And then now we have the time total being the sum of these two times. So none of this is right. We're going to have the time total equals this time plus this time. And then our problem now is to minimize the time. All right. And there's an example problem in the section that talks about this. Isn't that right? That you can kind of read that example problem and it kind of shows you a something like this. And so then we need to minimize the time total. So we're going to take dt total dx, and then we're going to get this derivative, and then we're going to set it equal to 0. Chain rule. And then this one, you can just distribute the 1/3. You get 2 minus 1/3 x, and you get minus 1/3. So let me. And then set this to 0. The 4 and the 2 reduce. And then we solve this equation for x. And we come back to part B now. If she walks 3 miles an hour, what's the minimum speed at which she must row so that the quickest way to the restaurant is to row directly with no walking? Alright, now I think I'm going to get added insight if I go all the way here. So let me put the 1/3 1/2 x over the square root of 16 plus x squared. Let's cross multiply. So I'm going to get 3x equals 2 square root of 16 minus plus x squared. I'm going to square both sides. Okay, subtract 4x squared. divide by 5. Take the square root. I'm only interested in the positive. And then I punch this out of my calculator. And then take the square root, and it's about 3.58 miles. So, although it's 6 miles, she would aim about a little more than halfway to be optimal for this. Now, by the way, this problem is kind of complex, but it's the same problem as if you see it like, think of it like this. Suppose you're walking along a shore, and you are here, and you have a stick in your hand, and your dog is with you. Here is a dog, and you throw the stick way out here. The dog swims, almost all dogs swim slower than they run along the shore. But if the dog runs all the way to get perpendicular and then swims out to the shore, that's not going to be the most efficient way. It's not the quickest way to get to it. The dog wants to go part way and then swim out. It's the same problem that we were just doing, just set in a slightly different context. And this made big headlines. And the headline in the newspapers when they did this experiment with real dogs was, the headline was, "Dogs Know Calculus." Because it turned out that when they threw the sticks into the water and watched where the dog would depart from the shoreline, that the dog would depart at precisely the point that was going to be the most efficient. And the only way that humans know how to compute this is by doing calculus. So the projection was, oh, the dogs must know calculus too. Of course, they're just using instinct, but it's very interesting that their instincts were precise on this. They departed the shoreline at just the right point to be able to minimize the time before they got to the stick. Alright, now, part B, we have to look at this problem we might set it up rather similarly. She walks 3 miles an hour, minimum speed, she must row. So that the quickest way is to row directly. Alright, so when we were doing this, the rate at which she was going, the 2, wound up showing right up here in this equation. And the 2 shows up right again down here. What if this number was different? If that one was such that this would not give you a real solution over here. Now the 2 there so one way we could look at this is replace this 2 with a constant, let's call it b. And if we replace it with b, this is going to be time. Let me go to a different color. Time total would be 1 over b. Everything else is staying the same. Now, dt total dx is 1 over 2b. And then when we set this to 0, bring the 1/3 over. Well, let me put this down here. And then we're going to cross multiply. Equals 3, and then we square root square both sides. Jump down. So x squared is equal to 9 over 4b squared minus 16. So we can see that x will be the square root of this. But if this thing is, as long as this thing is positive, we're going to get a real answer. And then x should be a positive number. You should move to the right somewhere. But we want the x to be 0. For the x to be 0 means you're going to row directly into the shore. Actually, let me not do it that way. We'll just do minus 16. Alright, so then we'll solve this. 9 over 4b squared is got to equal 16. Set that equal to 0. Cross multiply. 64b squared is equal to 9. B squared is equal to 9 over 64 take the square root of both sides, 3 over 8. So then B, way back up here, where, yeah, 1 over B. So B was replacing the 2 miles per hour. And if we replace it with 3/8 of a mile per hour, then she rose so slow that it would be better to go directly to the shore and then walk. That took up a long time. And we are at our break time now. So let us start again at $12:47. And I was going to show another optimization problem, a more complex one, but this one was quite a complex one. So when we start after the break, I'll start with just questions that you have on review, and we'll do review questions then. So see you in a little bit. Oops. What are you eating, Chase? Okay. All right, welcome back, and we're going to start again, and I checked the answer on 27B with the back of the textbook, and my answer on 27A agreed, but the answer on 27B did not agree. And so I looked up the solution manual, and I saw that I had made a mistake. And where I made the mistake was right here. When I took the derivative of this, I forgot to use the chain rule. And so the derivative is 1/2 times the 1 over b, 1 over 2b, this to the negative 1/2, and then times the derivative of the internal, which is 2x. And so this is going to change the answer, and so on. So I put some notes in here about changing the answer and going along. So, all right, but we spent enough time on that problem. And let's go on now to questions on, as you're doing the review for the final exam. Today's our last regular day. Final exam is tomorrow at 11:30. It opens up. And questions?
I have a few.
Okay.
Number 45 on 3.4.
Okay. 3.4. And let me look at the directions on that. Find the derivative. Okay. 45. Too small. Let me blow it up. Alright. So we have this, and we need to find g prime of z. G prime of x. And the first question then is, what rule do I use first? I see a product rule, because this x plus 1 times e to the x. I also see a division sign divided by x minus 2. So what do I have to use first? The product rule or the quotient rule?
The product rule?
Alright. The only way we can use the product rule first is by ignoring this part. We'd have to ignore the entire denominator. And that's not allowed. To take the derivative of this, we have to be able to use one rule that encompasses the whole thing. If we took all of this together as the numerator can be as complicated as we want, and the same thing as the denominator. Then we have a quotient rule problem without ignoring anything. You do the product rule, the only way to do that is to ignore part of the problem. So it's quotient rule first. So it's the bottom. Remember in the quotient rule, I like this arrow. The bottom times the derivative of the top minus the top times the derivative of the bottom. Now the derivative of the bottom is just easy. That's a 1. All over the bottom squared. So when I take the derivative of this one right here, oh, it's going to be complicated. That's a product rule. So I'm going to get, so this one is first times the derivative of the second. When I take the derivative of e to the x, I get e to the x plus the second times the derivative of the first. When I take the derivative of the first, I get 1 and then this I can distribute the e to the x to both. And then on the bottom I have this. And then that's pretty much it. I'll just do a little bit of cleanup here. And in this bracket here, an e to the x is common to both. So that could factor out. What would be left over is x plus 1 plus another 1, which is x plus 2. And that would be it. It's about as simplified as I can get that. You could factor out an e to the x out of both of those, but that's just a formatting issue. Kylie, does that answer your question?
Sort of. So I didn't understand how it got a 5 in that numerator.
You mean the book's answer?
Yeah.
It has something different than mine?
Yeah, it says e to the x times x squared minus x minus 5, I think. Let me check.
Alright. They could have foiled these two things out. Alright. Let me do one more thing. There's an e to the x common to all three terms in the numerator. And then if I foiled this part out right here, this becomes x squared. The two middle terms cancel each other out. Minus 2x plus 2x. Minus 4. So this all becomes that. And then this is e to the x squared. These two cancel out, you get this minus x. Minus 4 minus 1 is minus 5 over x minus 2 squared. So that's probably as simple as I can get it, right to here. If you gave me something like this on an exam though, I'd be okay with that.
Okay, thank you.
You're welcome. All right, another question. Okay, and the next question, I'm going to do it a little bit different. I'm going to have everybody work on it for a minute first. Even if you've done it before, I'm going to have you work on it fresh for a minute, and then I'll show it. So,
I mean, I had more questions, but I didn't want to take all the time.
Anybody else can interject? But go ahead with another one, Kylie.
Well, I had difficulty on 3.8. And it's number 31.
Okay, so this is to solve by implicit differentiation, and all right, so let me give everybody a couple minutes. Solve this one by implicit differentiation. Even if you've already done it, take a minute, do it again, fresh, and then I'll do it. So I'm going to take d dx of both sides. When I take the derivative of the left-hand side, derivative of sine of something is cosine of that something, then I have to chain on the derivative of the internal. And the right-hand side, d dx of x is 1, d dx of y is dy dx. Then this is probably the hardest part of this one. Taking that derivative via the product rule, And let me just give 30 seconds. If you had gotten to this point but hadn't taken this derivative, give you a minute, give you a little bit of time to get ahead of me. So it's the first times the derivative of the second plus the second times the derivative of the first, which is just 1. So then I get rid of the parentheses. When I multiply these out, I'm going to put the x up front. And put the y up front. Now I have two of my terms containing dy dx, this one and this one. So I'll bring them to the same side. So all the dy dx terms will be on the left. And then this one gets moved over to this side. Like such. And then I'm going to factor out dy dx. Finally, I'll divide both sides by what's in parentheses. And I have that. So, any questions on this one? Okay, any other questions?
Could we do 4.3? Number 73.
Okay, that's what section again?
4.3.
4.373. Okay. Okay, determine the intervals with concave up and down. And so it's this one. So for the intervals of concavity, we're going to need to just focus on the second derivative. I'm going to rewrite this as x to the 1/2 ln x. I'm going to have to get f prime and then f double prime. This first times the derivative of the second plus the second times the derivative of the first. Now, this derivative of ln x is 1 over x. And then ln x, the derivative of this is 1/2 x to the negative 1/2. Okay, so we'll simplify this as much as we can. Subtract the exponents, you get negative 1/2. Plus, and I'm going to rewrite the order. It's like such. Alright, so that's the simplest way I can rewrite f prime. Now I'm ready to take f double prime. Negative 1/2 x to the negative 3/2. Multiply these two together. Hold on a second. I screwed up. I was failing to see in this problem that this is a product rule. I'm going to have this be the first and this be the second. Plus first times the derivative of the second. If I take the derivative of ln x, I get 1 over x. Plus the second times the derivative of the first. If I take the derivative of the first, I get negative 1/4 x to the negative 1/2 minus 1 is negative 3/2. Okay, so then let me clean this up a little bit. And then I'm going to set the second derivative to 0 after I clean it up. These combine, because this is really x to the negative 1, add the exponents, negative 3/2. And I'll put that in a better order like that. Alright, so we found the second derivative. Boy, was it complicated. Now we set the second derivative to 0. When I set it to 0, I'm going to have to solve this equation. There are 1, 2, 3 terms. Terms are separated by addition or subtraction. What's common to all 3 of these terms? They all have a 1/2. Well, actually, no, these two cancel each other out. That's really nice. Alright, so before I do this, let me just rewrite f prime prime of x is this. This is pretty simple. Okay, now we're going to set it to 0. Okay, now this is really the same as this. The 1 gets absorbed times ln x. On the bottom is a 4 and an x to the 3/2. Alright, so for concavity, we're going to say that the inflection points are the values of x. Now, you have to look at two ways to look at it, whether the second derivative is 0 or whether the second derivative doesn't exist. ln x, well, x is not allowed to be 0. Can ln x ever be 0? E to some power, what's the exponent to get something, to get e to that exponent to be 0? It's impossible. So there's no solution, there's no way to get the numerator of this fraction to be 0. Okay, so this is never 0. This will be 0 if x is 0. Alright, so the inflection points, there's only one, and that is when x is 0. So, we look back at this function. This one is not even defined when x is negative, because ln of a negative number doesn't exist, square root of a negative number doesn't exist. And so this is the domain of this function is x greater than 0. If x is equal to 0, e to what power is 0, ln of x doesn't exist. Alright, and we found that it doesn't have any inflection points in the domain. But this is not in the domain. So there's really no practical inflection points. So the thing is, it's going to be always concave up or always concave down. And the second derivative, if we look at it here, ln x is positive. E to what power?
Could
Yes.
I don't know if this is wrong. I got an inflection point also. One can't, if x is 1, wouldn't that set the numerator to 0?
Oh, you're right. I did not see that. Zero if x is 1. Because e to what power is 1 will be 0. That's right. Okay, so inflection points, that's x equals 0, not in the domain. The other one, x equals 1, is in domain. So, the only real inflection point is x equal 1. Alright, so then, this function is only defined from 0 to 1, and then it's also defined from 1 to infinity. It's going to be concave either up or down on each of these intervals. Okay, so we'll come back to this one. If I plug in a really small number like 1/10, e to what power is 1/10, it's going to be a negative power. So if I just plug that into my calculator, and then I'm going to have this be positive, double negative will make it positive, so this is concave up. If I put a number bigger than 1 into this for the f prime prime, like a million, ln of a million is positive, this is all positive, but the whole thing is negative. So since it's negative, it's concave down. And that's my total answer. Any questions on this problem? All right, any other questions? All right, if there are no other questions, we will end class early today, first time in the semester, and we'll see you online tomorrow at 11:30. There's no need to be in Discord. You can just, but the final exam will open up at 11:30 tomorrow morning, and you'll have until 1:45 to complete it and upload it. And I'll check my email and Discord if you have questions in between now and then. Otherwise, I will see you virtually tomorrow. You're welcome. Let me stop the recording.